in most common contexts. That's why it's not only a number, it's a whole vector then. Okay, now if we have such a text, and let's assume it's green now, we have to represent it by a way that our learner can take it. And the simple thing you can do is the bag of words. Just a bag of words means we count the occurrences of each word after cleaning and assign just a number to each of these words and count how often they come in the text. For example, for this text snippet, for example, what do we have here? The sun is shining and the weather is sweet. After cleaning, probably the is would be away, but here, for example, it's here. We would count the number of is. And this gets a number here. That's the vocabulary. And we count how often this is there. For example, here, it's 2 times. It gets the number 2 in our vocabulary, and this says, okay, is in the third sentence is twice. The occurrence is twice. And if you do this over all text, you of course get a huge vocabulary, but you can sort that vocabulary given this bag of words counts. And then you know which word is most frequent. Let's say, of course, all the stop words are most frequent. Let's assume we have skipped them. And then the next most important word would be the top on the list of this vocabulary. The currency, if we count them and select them, we could say, okay, if we want to now do a representation of this text, let's take the most frequent words. And then we represent each text snippet, like each Twitter message, by the numbers of occurrences of the most important words in my vocabulary. You cut this at some point. And the bag of words is just a representation for single words. And we would select, given a database of text samples, the most important vocabulary of all these text data by sorting actually the occurrency of these single words within a text. And assign a vector, that's the bag of word vector, to some of these texts. And then we represent the text by a vector with the number of occurrences of a given word in the vocabulary as a vector of a back vector. And what we can do is we could do even more. This is now called, if you look at only one word, this is called a 1 gram. So it's a single word without any correlation. And sometimes it makes sense to look at 2 consecutive words. And this is called a 2 gram, or 3 consecutive words. It's called a 3 gram. Of course, they get sparser and sparser. It's not very often that 3 words, the same 3 words follow each other. But for example, the frequency of 2 words is not so sparse. And then you could also use here as an input vector 2.2, and you would also select all 2 grams. And you could also sort now the 2 grams. So the number of 2 consecutive words, and you sort them according to the occurrency of your text data, and assign actually a vocabulary based on the most frequent 2 grams in these texts. And then you know, okay, often this word comes together with this, sun and shining, and probably you see, okay, this is an important 2 gram. Probably not a good representation. I think let's stop here for the moment. I will continue after this text. We go now further because the bag of words is not the best representation of text data because it just counts the currency of a word. Given the big sample of text snippets, of course we can then sort out some unimportant words, but this is not the best way just to represent a given text. Okay? Are there any questions? Good. Then let's make 5 minutes break. Okay, next week I'll start at 1 o'clock and 10 minutes, so 1:10. I started too early, I'm sorry for that, because I had in mind we start at 1:05, so I'll start at 1:10 next time. Okay for you? Good. Okay, now a better representation for the, let's say, the weight of a word in the text is the term frequency inverse document frequency. And the idea is actually that not the absolute count of the words within a text is really relevant, but it is also important in how many texts does this word occur or happen or be. For example, is. If I don't kick that one out, I can assume, okay, the verb is or be or so, it will appear in every document. So counting these numbers of is or be does not make any sense. For example, I cannot classify, given that feature, the number of is in a text. But if I look at words which are really specific for one snippet of text, this is actually what I'm looking for. I look for specific words that classify kind of a text, represent the content of the text. And that can be achieved by term frequency inverse document frequency. And it is used to downweigh, to give it a lower weight, those frequently occurring words in feature vectors by scaling by the logarithm of the relative document frequency. Means, okay, I look first of all, how often does this term in the full set of text occur? And then I look for each term, how many documents are there which contain that term? And then I divide the those two, or more or less, and multiply this term frequency by the inverse document frequency. That's defined normally in this way. It's not unique, it can also be defined differently by the number of documents divided by 1 plus the document frequency where this term occurs. Term frequency, number of occurrences of a term in all documents, and the number of documents that contain that term. That's the document frequency. If we take the logarithm, the inverse logarithm here, we get this term frequency inverse document. And just here to mention, scikit-learn implements it a little bit different. This feature now for text actually is much more useful, for example, to classify text or to do a sentiment analysis. This is one feature, would be one feature which you could use. It's this IDF. Let's talk about the TDIF. Okay, then this is the whole chain we would use by, for example, doing a pipeline. We transform documents, we transform them like features, numeric features. Once we have transformed them, we have those numeric features, and we can apply actually a fit procedure or a machine learning algorithm. It could be a classifier, any classifier, and we would also use a predict to get, for example, the expected label of a text to say, okay, this was a benevolent message or a Twitter, which means it was good for me, or this was quite a hard critic. And we could sort these texts automatically out. But we have first to generate those feature vectors. Of course, if we have now generated a lot of feature vectors, we have to find a way how to select the best. And that's where we now come into feature selection. And this is the next topic. I just mentioned here, there are 2 books here from Pract Publishing, or also here references to courses specialized for natural language processing. You can have a look at that. It's quite interesting. Or how to deal with an LTK. In scikit-learn here, we have the following things: count vectorizer, the hashing vectorizer, the TF-IDF transformer, which we looked at, and the vectorizer. This is actually now feature generation for text. Good. How can we select now the most relevant features? Why do we do it at all? We want to reduce overfitting, so we just take the relevant features for our task. and for this we get better generalization, and more or less we get also, which is called kind of inference for ourselves, the importance of these features. We learn something about data by selecting the most relevant one. And these two goals are coupled together. We will look now at univariate feature selection, linear models, tree-based models, and recursive feature elimination as 4 methods how to select relevant features. Okay, in univariate feature selection, each feature is looked at per se, alone. And what we look at is actually feature importance by doing kind of a regression model. It's kind of an ANOVA test that we do, analysis of variances. Or we look at the Pearson coefficient and say, when we have a linear model, how well does this feature correlate to the output data? What is the Pearson coefficient? Of course, this only works normally for linear models, linearly correlated data, and we have to also find a thing how we can deal with nonlinear correlated data. Okay, here are the methods that normally are used. F regression, and we come to this, the mutual information regression. This is a generalization for nonlinear correlations. And for classification, we have similar methods to select features in an univariate level. Each feature individually, not coupled together. Okay, the Pearson correlation coefficient is defined like this. And this already gives for linearly correlated output values to input values a measure how important it is. After we have scaled, we really can look at the absolute value of the rho to say, okay, this is more significant than another feature because it has higher weight in linear terms. Because after we have standardized, normalized the data, all the weights can be compared. If we don't do a scaling, a normalization, we cannot do that, but now we can. The drawback of the Pearson correlation as feature ranking is only sensitive to linear relationships. And there are many non-linear relationships where we still would say the data is correlated. And here are some examples. This is the Pearson correlation coefficient for this kind of data. And for linear correlations, we look like that. So we say, okay, it's totally negatively correlated, totally positively. And then we add some noise. We would say, okay, then it worsens, it gets worse. It doesn't depend on the slope. It's more the linearity that we look at. But here, for example, the Pearson correlation coefficient is absolutely 0. It's a pure 0. But we know that the data is correlated. It's highly correlated. If we plot that in a polar coordinates system, which has an R value which is constant. And there is correlation in this data also here. So the Pearson correlation coefficient is not able to capture these dependencies. And we need something better. And something better is the mutual correlation coefficient. And what it is actually the weighted logarithm of 2 probability distributions. And for example, this here is the joint probability distribution we'll look at next time, especially on what it is, compared to the 2 marginal distributions, which are actually the integrals over the other variable, and only depending on x. And it shows, okay, if I look at each feature individually, or if I look at the joint probability distribution, it looks at how much can be explained by these 2 features alone without correlation. That's how I would interpret this mutual information coefficient. So it's like a Kullebach-Leiber divergence of these probability distributions here. And we can also use it for non-linear correlations. And it's not that easy to apply it. Sometimes you have to apply binning. And another method is the maximum information coefficient, MIC, which can then be used to cope with things where we have less influence on the discretization of the data. This is so even a better method to get this non-linear. Here you find it in the min-epi library of Python. So this is, correlation is there, even if it's not linear, and we could get it out by the mutual information condition. We can also look now each feature itself, now with univariate, so we look at each feature independent by fitting actually a model based on this input, on this feature itself. And here I use a random forest regressor, for example, and look at the importance of these features. We have here a bagging of about 20 estimators. We limit the depth of the tree to 4. And then we calculate the cross-validated score. Here, it's 3 times cross-validated, cross-master 3. And look at now at the Pearson coefficient, at the importance of these individual features on the regression tree. If we can make a list, a sorted list about the importance of these features. This is now still univariate. And here we are not limited to linear ones. A regression tree is far away from being a linear model. Now we go back to linear models and use regularization for a second method for feature elimination. Especially actually the L1 penalty is useful to skip some features out because the L1 penalty has edges on this norm ball. And often the minima of the optimization procedure are taken at the edges of this norm ball, which looks like a highly dimensional diamond in n-dimensional space. So it sticks to many edges. And if I stick the minimum to an edge in this optimization problem, I skip features out. Okay. So rather than using L2 regression or the ridge regression, we look at the lasso regression and kick those out here that have a coefficient of 0. Here's an example. We load the Boston data. These are the Boston house prices data. We do a scaling and fit the linear model using here a lasso regression, L1 norm with a coefficient of 0.3, the lambda is 0.3. And what you see now here, the last line shows that actually this one, tax, the rate, the age, Indus, they fall out because they have a coefficient now in the lasso regression of 0, absolutely 0. And so we can, in first approach, just skip those. This gives also an indication, okay, they're not really important. And you wouldn't get this by a ridge regression where you have an L2 norm because this makes an average over all these features. It's like rather an averaging weighting of all the features rather than selecting the features. And L1 selected. Yeah, that's here. Huh? So L2, I would say it's probably more important for feature interpretation, and L1 norm for the regularization is more important or more useful for feature selection. That's it. Okay, tree-based methods. Did you have a look in detail at how a random forest works? Not really, huh? Not yet, probably. Okay. Then we have to explain a little bit. Huh? How does a random forest regressor work? Then, for example, even a backed one. So a random forest regressor takes a feature, looks at it, and decides, okay, is it good at separating out the classes so that I have a minimum impurity, that I can separate the class one to the other one. And it does this using different measures, and one measure of that is the entropy of the data set. And the entropy is big if there's a big disorder. And it's small if I can clean up quasi this class by this class. And so a feature that has a bigger information gain, which reduces the entropy more, is worth more than another. And that's the idea behind feature selection based on random forest, random trees. So we look at actually the importance of separating out many classes of a feature based on the entropy change that is employed at this stage of the decision level in a tree. Okay, normally three measures are used: the gene impurity, information gain, these two, or these two. For a regression tree, it's variance, that is the decisive criterion on one of the branches or the switches in a tree, the splits, to decide which feature is used best here to make the splits. We'll calculate it one for one feature. The entropy is defined by the negative logarithm p log p. Here, the logarithm of 2. It's an information measure. And the information gain is actually the change of the entropy at a given split after and before that split, given, for example, that feature. And we will now calculate it. This is quite a theoretical thing. We will calculate it on one example that you see how it works. Here we have actually a probability table, more or less. So we could generate a probability table out of it. We could use this information here, this information to predict whether we should go to play golf today or not. And we want to make a classifier out of that. And to do that, we look, for example, at one feature. The response is, should we go and play golf? And the feature we look at now is the outlook of the weather. How does the weather be? What is the weather outlook for tomorrow? It should be sunny, overcast, or rainy. Now we count on how many occurrences we have that we go and play golf if it's sunny. Then we have to go to this table and say, okay, sunny, how often do we play golf? We go twice. This is the empirics, this is the data we have. This is our data matrix. Okay, we fill it here. It should be 3. There should be another sunny. No, yes.
Sunny
It's only 2 in this table, right? If we go play golf, no, it will be 3, right? No, yeah. So we switch here. If it's overcast, do we play golf? Overcast, we have 4 yeses. This is correct. We have no. If it's rainy, we have 2 yes. Rain here and rain.
There's a third one.
And the third one, yes. Rainy.
So it's the opposite. We could switch it with sunny then.
Yeah.
Sunny
I
and
think
rainy.
this is a mistake here. These are flipped. Let's assume this is correct because I calculate on that table. So it doesn't reflect what's in here. I'm sorry. But now we calculate the conditional entropy. And what is the conditional entropy? Do we play golf given an outlook? And we have 3 possibilities for this outlook. It could be sunny, overcast, and rainy. So we have to sum all those entropys. So we take the probability that it is sunny. It's the weighted entropy split by 3 and 2. This is the entropy that we would get if you take this criterion, your sunny, to split the group. The entropy 3, 2 would be actually the sum of the logarithms here, it's defined over 3 over 5, log 3 over 5, plus 2 over 5 plus 2 over 5. So now we do this for the next feature and calculate the entropy given that one, for 0. This is the split for 0, and the split for rainy, it's 2, 3, given that thing. So this is 4, 5 over 14. The whole data consists of 14 entries, and the probability that it is sum is 5 over 14. So 4 over 14 and 5 over 14. This is the weighting of this conditional entropy. And the entropy is calculated by here the split, like this, 2 over 5 times log 2, 2 over 5 plus 3 over 5, always the complementary of it. Now the information gain is here. Information gain, should we play golf given the outlook, is the probability at all that we play golf minus the conditional entropy that we play golf given that feature outlook. And what we do is then we do such a calculation for every feature and select the feature to branch now which gives the highest information gain. And now we can, for every feature, we can track in this random tree how much information is added by this feature. We sum it up all over the branches of that tree. And then we get an information of how important such a feature is, because it helps to reduce the disorder. It adds information, and the more this information, the higher information gain is for a given feature over all these trees, the better actually the feature ranking is for this feature. And this is now shown here for the entropy. So entropy is coupled to information gain, which is the difference of actually we should go for golf after deciding given the feature outlook. Okay, and that's actually what we get out. And probably I give you now an example, a concrete example how it looks like. Okay, we have, for example, a model-based feature selection here using the Boston house prices here. And we use a random forest regressor and use as criterion for the selection of these features the information gain. And we can do it quite easily here. I instantiate here the random forest regressor. It is fitted to the data. Let's start. And now we print it according to their score. So it does it automatically when generating such a tree. It looks at how much information is gained by these individual features, which is just here. And of course it's nicer than to plot it, and you get a table like that. And where we see, okay, there are really two important features, this one, probably this one, we could rank it, we could sort it, and then decide on how many features we want to take with us, and use them only for example, doing a new regression. This is now not cross-validated, the whole thing could also be cross-validated. This is done only once now to get better predictions about the importance of the features. We should do it cross-validated.
The random forest using out of bag, so it's not a cross-validation, but
it's already averaged, right? Right. What we have here, this is the example from before, and yeah, here we come to this when we do feature elimination. This is now the next topic. How can we do feature elimination? Okay, this is the fourth method I want to just explain. The idea between recursive feature elimination is that we selectively or recursively kick some features out. So we look at them recursively, but still smaller sets of features, and train estimator, the regressor, again with less features. And so we get a ranking of the features. We pick out first actually those that attribute the least to actually our accuracy, and then we do the same again. And we can use it, it's already implemented here in different learners. We get normally this attribute feature importance, and according to this attribute here, and you have to look at in detail how it works for a given estimator, we can select features, keep the least important ones out, and then do again a recursive estimation, only using a reduced set of features, do the same again, and so on, until you would say, now I have selected 7 features, that's fine for me. Yeah? You have to stop at some point, and this is more or less what you give in at this moment. Okay. Yeah, this I could probably show, model-based feature selection. We also use it here. This is this here. What do we have? It's the same data set. It's the Boston house prices data set. I use a random forest regressor on this data set. And now we do a cross-validated search or loop here to split. And we have no cross-validation. This is what we had. And now here, using these two methods, recursive feature elimination, RFE, we can now recursively eliminate one feature after another. And at the end, you get a feature ranking like that. And it looks quite similar, but it's not identical, because you train your forest regressor again with less features. That's all. The first method, you just do it once with all features, and then you get a certain ranking. Here you do it recursively with less and less and less features, and get a ranking by this. This is the recursive feature elimination. Good. Okay. This is just a summary how we use it in scikit-learn feature selection. There's quite some methods here which we could use. Some are univariate. Here we looked at the recursive feature elimination at the end. This is just for you a summary of the methods that are implemented. Good. And at the end, I just want to add something. There's also a method called automatic feature generation. I'll just explain the idea behind it. It's actually so that we generate first a lot of features and use feature selection methods to kick them out. So first of all, actually, they are generated automatically, for example, by using correlation terms, generating those features, combinations of the features, and at the end, they will be reduced according to similar criteria that we looked at now. And there is a tool here, it's called feature tool, which can be used for automatic feature selection and generation. Good. Now audio signals. This is also an important kind of data, and it is not the most idea to just feed a raw data file, like a wave data file, into a machine learner. First of all, it's quite a lot of data, and it's probably not a good representation. It's not a good embedding for this kind of data. There are better ways to do that, because normally these data has to do with music, sound, or with voice. And we express our voice with vowels, for example, with consonants. And these consonants have a certain sequence, and they have a certain duration. And we can say that within a speech, actually there are time frames where our sound is more or less stationary. To spell an A, it takes some time. And during that time, you could say the sound at this few milliseconds, it is stationary. And it turns out that actually a good time frame for stationarity in spoken words is about 25 to 40 milliseconds. So the idea is actually to split up such a wave data in overlapping frames of about 30 milliseconds. And sometimes the overlap can be as much as 50%. So you have blocks of overlapping voice data, and with that you didn't gain anything, but what you could do is to look at the spectrum. Spectrum of the sound, which reduces actually the data size. And this is called, actually, we do a kind of a short-term Fourier transformation over these frames of, let's say, 30 milliseconds. And we get a spectrum out of it. This is actually justification. Actually, our sound is slowly time varying. So within these 30 milliseconds, it's more or less stable. We have a limited frequency range. Normal sound is below 7 kilohertz, so a sampling frequency is normally sufficient 8 kilohertz for recognizing voice and spoken words. 8 kilohertz would already be sufficient. Better would be 16 kilohertz. What could we do with that sound? We can, for example, identify a person who did speak. We can identify the sex of the person with male, female voice, or even we could assign a dialect to the spoken. So there are many things you can do with spoken words besides classification. These would be 2 examples of classification. Okay. The idea is now we clip the data in frames, overlapping frames of about 30 milliseconds. But within these 30 milliseconds, we apply a Fourier transform to get the spectrum of it. And the normal sound, it has kind of a basic frequency, the first harmonic, second harmonic, and so. This makes the sound quite soft, and our voice is similar like that. Or we could also see if I have consonants, these are normally very high frequent data. This goes up to 16 kilohertz or so. We can differentiate these already by looking at the spectrum. And the other, the vowels, O, A, E, they are quite low and have nice harmonics. So we can, by looking at the spectrum, already identify more or less the vowels and the consonants. And when we do that, actually we do something like called a short time spectral analysis. Now this is not all. Now our auditory system works actually logarithmically. And not only logarithmically in the amplitudes, but also logarithmically in the frequency spacing. So it makes sense actually to apply now filter banks that are logarithmically spaced. And a very famous filter bank for that is that MEL filter bank, which spaces the frequency in logarithmically spaced bands. And then we filter our spectrum by these MEL filters. So sometimes actually it's not, we don't talk about frequency in hertz, but in frequency in MEL. There's a kind of a pseudo unit which can be used when we think of a logarithmic frequency scale. The second thing is actually that also the amplitude is logarithmic. Our ear is very sensitive. The reference for 1 decibel is 10 to the power of minus 12 watts per square meter in intensity. So our ear is very, very sensitive. And how can it measure then a range of 0 to 120 dB? We see it, 120 dB. This is 10 to the power of 12. So 12 orders of magnitude our ear can perceive, can hear. And how can it do that? Just by applying kind of a logarithm. We hear actually in decibel. And that's also what we would do here. We would look at this power spectrum, so not at the phase, we could also do at that, but we actually calculate within these filter banks the power spectrum and take the logarithm of that amplitude as well, so that we have a spectrum in dB. And this spectrum is then used as an input feature for every 30 millisecond frame. And here you see this MEL spectrum. And here you also see that they are logarithmically spaced. They look like triangular filters that are applied as as envelope filters in the frequency range to this frequency spectrum actually, and at this point it's replaced by the sum over this triangle of this filters. This gives our MEL frequency component at this point. Now this is not enough. Often it's enough to do that we say let's leave it that, we just apply MEL filter banks, these logarithmically spaced filter banks, and we directly feed in these values as features for our voice recognition system, automatic voice recognition system. But it turns out, and you see that when you have a triangular filter, we have kind of a lot of higher order harmonics which are in still. Huh? If you do a Fourier transform of that spectrum of a triangle, you have all uneven harmonics in. So it's not really limiting here nicely to this band that we want to look at. To avoid that, there's a trick applied now, and this is really strange now. We apply now a Fourier transform to a spectrum itself. It's a special kind of Fourier transform, it's a cosine transform. So we take a cosine transform of already a Fourier transform signal. We do a double transformation. And then we're no longer in the spectrum range, we're called, what it's called, we're in this capstrum. It's called the capstrum, and it avoids the correlation between adjacent bands, because this is now avoided by taking the second spectrum of the spectrum, which is called the capstrum. And you see this is playing with the letter, with the word capstrum, spectrum. It's flipped. Huh? And if you work in the capstrum, actually, you do not filter, you do lift. You do lifter. Huh? So you change the words from back and forth. This is just an amazing thing. Huh? And it turns out there's now these coefficients, these MFCC coefficients, after taking the cosine transform of these already filtered spectrum here, this is quite a good feature for voice recognition. And these are called the MEL frequency capstral. Also, this is not a misspelling here, it's really called capstral coefficients, MFCC. Yeah, and they're used actually for voice recognition. Nowadays, also often on this level, directly feed in the spectrum after log transform of the frequency axis. This is actually, what do we have an SS difference between these two spectra? In the normal spectrum, you have all these higher harmonics. No? And by the second Fourier transform, or the cosine transform, you get them out. So all higher harmonics at the base frequency are reduced to only one feature. That's the idea behind this second cosine transform. Probably I have an example before I finish. Let's see. Let's try this one. Synapse is not fine. Yeah, I try to draw it probably during the exercises. For the moment, I can just show how it looks like. Let's say if this is now the time, because we have time frequency, and we have every 30 milliseconds here, we have such a block, of course, with overlapping blocks, 30 milliseconds. And if we have here a frequency axis in a logarithmic scale, in a logarithmic scale, we would have all higher frequencies, base frequencies, first harmonic, second harmonic, third harmonic, they're over each other. Huh? This could be an A, and then, for example, a consonant would be like that. It's more like noise. Huh? So there's not really periodic signals in it. Huh? And what the second discrete cosine transform does, it reduces it actually to this base frequency here. And then you don't have any more of this redundancy in the feature representation of the audio signal. But it's hard really to understand why this second thing this. It's kind of a decorrelation, and decorrelation of highly correlated signals by overlapping, first of all, filter banks, and the second thing, to also get rid of these higher harmonics, or to reduce it to one of these. These are the Mercapstrom coefficients. Right? What could we do with that? This is one example, for example, of a speaker identification. Who speaks this sound? Right? We could use here in this paper, it's shown robust text-independent speaker identification by modeling the voice of a person as a PDF probability density function based on several Gaussian distributions. So it's like a Gaussian mixture model to identify a speaker. And what has lately happened, this is a nice thing. Probably you've heard of this cocktail noise problem, cocktail party problem. If you're in a party, sometimes it's really hard to understand each other, even for us young people or younger people. For elder people, it's even worse. The technology today to actually do the problem of source separation, that's how it's called, is they do beamforming. Means that these hearing aids have multiple microphones integrated, and they use the phase information of the sound arriving at the hearing aid to focus in front. So the person I look at, I get the most sound back. And this helps a lot to reduce actually the noise of people speaking around, but it doesn't solve it totally. It turns out that when we